Alright team, so our experiment setup is rather simple. We have a fan blowing over this tub filled with water. What I will do is that we measure the distance from right here to right along there to be about 1 foot, very close to 1 foot. So I will drop the boat in the water at that marker, then time how long it takes to travel to the next marker to find the average velocity that the boat is traveling at. Okay, timer ready?
Yep.
And go. So we got 1.15 seconds for the first run. This is now going to be the second run. Timer ready?
Yep.
Release. 1.39 seconds. And third trial is right now. Timer ready?
Yep.
Release.
1.39 seconds.
1.39 seconds.
So as we run more trials, the bottom of the boat gets more wet, which means that more of it is gonna be submerged in the water, which means it's gonna take longer for it to travel because there's gonna be more forces acting on an area that is submerged. So for the calculation, we're going to start by finding the area that the air acts upon for the boat. So then using these dimensions that we found a total area of 10.45 square inches. And then for this, we're going to assume that all of the area is above water, even though a little bit will be submerged. But it's just simpler if we assume it's all above water. So then drawing a side profile of our boat, we're going to have a velocity from the air acting what we're going to assume to be horizontally onto the side of the boat. We're also going to have a velocity of the boat moving across the water. So here's our water. And then we're also going to have a force acting in the opposite direction on the opposite side of the boat. So using linear momentum, we can write an equation here saying that the sum of the relative velocity times the mass flow is equal to the sum of forces acting on the body plus the sum of forces acting on the surfaces. Which we can rewrite because we want to find this force acting on the opposite side of the boat. We can write that is equal to the relative velocity squared times the density of air, because we're going to assume that all this area is acting in the air, times the area that the air is acting on the boat. So finding this relative velocity, we know the velocity of the air acting on the side of the boat, and we're going to conduct 3 trials to find an average velocity that the boat is moving. But first, finding this velocity for the air, we looked up the specifications of the fan to find an air flow rate equal to 2,800 cubic feet per minute. Which we're also going to find equal to 46.67 cubic feet per second. Knowing that Q is equal to velocity times area, and knowing that the area of our fan has a radius of 1 foot, we're going to find a velocity for the fan, or the velocity of the air here, which is equal to 14.85 feet per second. In our video, our fan was tilted a little bit, but we're going to assume that this is all acting horizontally. So then for the velocity of the boat, we conducted 3 trials to find an average velocity of the boat equal to 1.31 seconds, and that was across a length equal to 1 foot. Sorry, this is not the velocity of the boat. This was the time that it took for the boat to go that 1 foot. So that was equal to 1 foot divided by 1.31 seconds, which is equal to approximately 0.76 feet per second. And this is the velocity of the boat, or the average velocity of the boat. So then finding the relative velocity, that is going to equal the velocity of the air minus the velocity of the boat. So that's going to be our 14.85 feet per second minus 0.76 feet per second to find a value of 14.1 feet per second. That's what we're going to use in our equation here. So in finding that value, that force acting on this side of the boat, that's going to be our 14.1 feet per second squared times the density of air, which we found to be 0.0023769 slugs per feet cube. We're very precise here. And then also multiply that by the area that the air is acting upon, which is 10.45 square inches, which we need to get into feet. So we're going to divide by 144. And that results in a force of 0.034 pounds. And that is the force acting on the side of the boat. And that is it. That is using linear momentum.
Okay, so we got 1.15 seconds for the first run. We're just going to do it a couple more times just to get more consistent results. Timer ready?
Yep.
And release. You see, that one was a dud.
We throw that one out. There's some laminar flow. And towards the end, turbulent flow.
So as you can see here, you can see my finger behind it very clearly. As light passes through that flow, you could obviously tell that it is very laminar, just because of how visual my finger is. Can you hold it, please? And then as you approach the bottom, my reflection becomes more and more distorted. Alright? This is an indicator of turbulent flow. And then obviously as it enters the water, you see the bubbles, you see the chaotic stream. That is turbulent flow. You got laminar, and you got transitioning to turbulent as it goes along the stream.